Another day here in related rates. We're going to start with going over problem 28 from the homework. So in this problem, we have two sides of a triangle are 12 and 15. The angle between them is increasing at a rate of 2 degrees per minute. The question is, how fast is the length of the third side increasing when the angle between the sides of fixed length is exactly 60 degrees? Let's go ahead and organize some information. Here's a diagram that I used to figure out what was going on. I've got my triangle, sides of 15 and 12 meters. I know that there's some angle between there that's increasing at a rate of 2 degrees per minute. I don't know exactly what the size of that triangle is at any given time, except for I'm interested in when it's 60 degrees. And the side across from that angle is going to increase as the angle increases. I need some variable for that. I chose x. So for this problem, in terms of the variables we have on the screen, what are we given, and what's given and what's unknown, basically? d theta dt is given? Is what? That's 2 degrees per minute. Okay? What's unknown? dx dt is unknown. Yeah. At some point, I'm going to have to convert the degrees to radians, so I've already done that. The 2 degrees per minute is the same as pi over 90 radians per minute. And the unknown is dx over dt when theta is 60 degrees. Okay? I've gotten to the point where now I need to just come up with a function or an equation that I can work on that relates theta and x. And most of you guys saw what that was. Law of cosines. So law of cosines will tell me that x squared equals 12 squared plus 15 squared minus 2 times 12 times 15 times cosine theta. Straight out of the law of cosines. I can work on that a little bit and clean it up. So x squared equals 369 minus 360 cosine theta. At this point, I still know that I'm interested in dx dt. How fast is that side changing? In order to get that, I can take a derivative. So go ahead and differentiate both sides. The derivative of x squared is 2x dx dt. The derivative of the 369 is 0. The derivative of a negative 360 cosine theta is going to be positive 360 sine theta times whatever the derivative of theta is. We need to see theta as a function that's inside the cosine function, so we need to follow the chain there. Where'd the positive come from on the 360? Yeah, the derivative of cosine is negative sine. So the negative times the negative makes it positive. Say that again? That's correct. The derivative. Exactly. Yeah. So far, so good? Now, when I was watching you guys and helping some of you, I noticed that there was a major confusion on the degrees radians thing. This sine of theta, I can put anything I want to into that theta. I can put in degrees, I can put in radians, I can put in gradients, I can put in whatever. I just tell the calculator what I'm putting in when I put it into degree mode or to radian mode or to gradient mode. Okay? That's what that degree and radian mode is for, is you're just telling the calculator what angles you're putting into the sine, cosine, and tangent functions. But this d theta over dt, that's just a number. It's times a number. So I can't write 2 degrees there. I have to write a number there, and that's why we've done the conversion from 2 degrees per minute to pi over 90 radians per minute. Pi over 90 radians is a number. It can be used in calculations. It's not just an angle measure like 2 degrees. So when we do the substitution later, you're going to see sine of 60, because I'm going to leave my calculator in degree mode. That's okay. But you're going to see pi over 90 radians going in for the d theta dt. I need to divide both sides by 2x to get the dx dt by itself. I'm going to need to know what x is. So what I'm going to do to figure out what x is I'm going to look right back up at this line right here. Because x squared equals 369 minus 360 cosine theta. When x is 60 degrees, or excuse me, when theta is 60 degrees, I'm interested in x at that point, right? So I'm going to take 369 minus 360 times cosine of 60, and then I'm just going to square root that, or I'm just going to leave the square root on it and keep the exact value. Cosine of 60 turns out to be a half, doesn't it? So if I take 369 minus 180, that's going to give me what? 189? So x squared equals 189, therefore x would equal root 189. So when theta equals 60 degrees, we just found out that x is going to equal root 189, positive or negative. Can x be negative for this problem, for this context? X represents the distance of that side, so it needs to be positive. So we're going to keep the positive root 189. Therefore, plugging back in, dx over dt equals 360 times sine 60 degrees times pi over 90 divided by 2x, which is now root 189. We can go ahead and put that in a calculator and get an approximation to whatever degree we want. So it's about 0.396 meters per minute. Okay, here's a problem for you to try. This might take a little while, and you might want to work in small groups even. But see how far we can get with this here in the next 10 or so minutes. If you're working at home, now's a good time to pause. When you're ready, check your answer with ours, press play.